We have already studied discrete time arrival process, a typical example, Bernoulli process in detail. We have seen for the Bernoulli process, first arrival time, which is a geometric random variable, then the number of arrivals up to time n, which is binomial, then arrival times, which were Pascal, and inter-arrival times which were geometric. Those things we have seen along with few examples to illustrate all of that. Now let's come to the continuous time arrival process. So for studying continuous time arrival process, so here the arrival happens continuously over time. The arrival can happen at any time small t from 0 to infinity. Two approaches are possible. One is to have a discrete time approximation. For many examples that might work. So then the Bernoulli process will be enough. For example, if you look at the traffic accidents in a city and assume that the city is not very crowded city, it's some interior city. So there you know that the accidents are very rare. So the entire time interval you can divide into say minutes. So your one time slot means 1 minute. Next time slot means next minute. So you can actually divide. If not minute, it can be half minute or it can be 2 minutes. It depends on the particular city and the record available on the city. You can decide which is the correct time slot, length of the time interval to be divided in that. So then you can actually record an arrival in this discrete version. When first minute an accident happens, you call it as x1 equal to 1. Otherwise x1 equal to 0. Then in the second minute, it is that means after 1 minute, the second time slot, then it is x2 equal to 1 or 0 and so on. So it is a Bernoulli process. But how to choose the length of the small time interval? Here in this example, I am telling 1 minute, but it can be 1 second or half minute, anything. So if from your data you can make out an appropriate small time length, then we can go for discrete model, which is Bernoulli process, and you can do all the analysis with that. You can keep track of the number of accidents by this much time and number of accidents within this time. All that we can do with Bernoulli process. Now, there are many problems where finding the correct length of the small time interval, it's not very feasible. For example, if we have a very bustling city like New York or Mumbai, where a traffic accident can actually happen at any time, you cannot really consider any small time interval. In those kind of arrival processes, it is better to keep the time t as a continuous variable. So in that example, we will have an analog of Bernoulli process, the continuous time, which will be called the Poisson process. We study time homogeneous arrival process in continuous time. Continuous time homogeneous arrival process. So we say that a process is time homogeneous if in determining the number of arrivals or nature of arrivals in a particular interval, the interval position is not important. Only the length of the interval is important. So whatever, for example, we look at the interval say 1 to 2. Whatever arrivals which probabilistic nature in this interval 1 to 2 is same as you look at the interval say 50 to 51. So only the length of the interval matters. Such processes are called time homogeneous. So we study time homogeneous arrival processes in continuous time. It will be helpful to have this notation to define formally a Poisson process. We will use it throughout this chapter. P of K auto. So K means the number of arrivals. K can be any number from 0, 1, 2, etc. Tau is the length of the interval, because we need to look at only the length of the interval, not actually the interval, because we are studying only time homogeneous processes. So for any non-negative integer k and any positive number tau, you look at pk tau, which is notation used to notate the probability of exactly k arrivals in an interval of length tau. Okay, so this notation is very crucial in the following definition of Poisson process. So in the Poisson process definition, we also will use something called lambda. So lambda will be a positive parameter. If you remember the Poisson random variable, it has a parameter, positive parameter lambda, and the Poisson random variables mean and variance both are lambda. So this lambda will be called, for the Poisson process, arrival rate or intensity or arrival rate of the process. So it is analog of the corresponding P parameter for the Bernoulli process. See, for the Bernoulli process, this P, which is actually E of x1, which is equal to E of xn for every n, right? It's a Bernoulli random variable which takes 1 with probability P and 1 minus P with probability, the Bernoulli random variable which takes value 1 with probability P and 0 with probability 1 minus P. Therefore, its expected value is P. So in that sense, in one particular time slot, you look at one time slot in a Bernoulli process, say nth time slot, the arrival rate is P in a sense, in one time slot. So that P is arrival rate in the Bernoulli process in that sense. This lambda in the Poisson process definition will play the same role as the arrival rate for the continuous time Poisson process. Let us now have the formal definition of the Poisson process. So a continuous time arrival process is called a Poisson process with arrival rate or intensity rate lambda. So lambda is a given positive parameter. If three conditions are true, the first condition is time homogeneity, about which we have discussed already. Still we repeat, the arrival process. First condition is that the arrival process is time homogeneous. That means that the pk tau, the probability of exactly k arrivals in an interval of length tau, that is same for all intervals of the same length tau. Right? Only interval length matters, and this should hold for every k equals 0 or 1 or k. So fix k, then pk tau depends only on the length of the interval. And this is true for every k. Okay. Time homogeneity. So this assumption corresponds to the Bernoulli process assumption that in each time slot the arrival distribution is same. There it is Bernoulli with same parameter P, right? So it is distribution of the arrival is same in each time slot. So this is analogous here in the continuous time case. Now second property is independence property. It says that arrivals in disjoint time intervals is independent, probabilistically independent. If you know that this many arrivals has happened in this interval, what are the arrivals or with what probability how many arrivals will happen? Any probabilistic information about future time arrivals or even past also disjoint intervals, we will not have any say on that by given this knowledge. Okay. So arrivals in disjoint time intervals are independent. Okay. So this corresponds to the independence assumption on the Bernoulli process for the discrete time case. Right? Each x1 is independent of x2, x2 is independent of x3. If you look at the all family in the Bernoulli process, x1, x2, x3 and so on, then their family is mutually independent. So this is the analogous assumption here. Then finally the third assumption is that So you look at the probability of exactly k arrivals in interval of length tau, k equal to 0. That means p0 tau. Probability of no arrivals in a given interval of length tau, it is approximately 1 minus lambda tau. Where O of tau means a small o of tau, which is the famous, right? So small o of tau actually means limit tau tends to 0 of tau by tau, right? This is equal to 0. So this is like in the Taylor series expansion, the higher order terms from second order times third order terms put together. So this is the small o of tau. Then similarly for k equal to 1, the probability of exactly one arrival is approximately lambda tau, or the plus negligible term. And probability of having two or more arrivals, it is in a given interval of length tau, is actually negligible if the tau is very small, because we are all talking about O of tau terms when tau is very small. Okay. So this corresponds to the assumption. So you look at the probability of zero arrival in any given interval of length tau. Tau is very small. It's approximately 1 minus lambda tau. So this lambda tau plays the role of the parameter p in the Bernoulli process. The probability of exactly one arrival is approximately lambda tau. That's p and 1 minus p. So this plays the role of parameter p here. And lambda times tau. Lambda is the intensity, arrival rate, and tau is the length of the interval. Okay. That's why it is called lambda is called the rate of the Poisson process. So for a Poisson process with rate lambda, recall that pk tau is the probability of exactly k arrivals in an interval of length tau. I am just writing interval 0 to tau, but instead of 0 to tau, I can replace the interval 0 to tau by any interval of length tau, 100 to 100 plus tau and so on. So this was our notation. Actually, this probability pk tau can be written in an equivalent way. So that will be helpful for us. For that, you define n tau. Tau is any positive number. N tau is a random variable, which is nothing but the number of arrivals in the interval 0 to tau. So instead of the interval 0 to tau, suppose you take the interval tau to 2 tau. This n, the number of arrivals in the interval tau to 2 tau also will have the same distribution, or 100 to 100 plus tau. They all have the same distribution. They are all identically distributed. So n tau is that random variable which gives you the number of arrivals. If you recall, for a Bernoulli process, the number of arrivals from 1 to n, that was a random variable which had a binomial distribution. Okay. So here it is interesting to find what is the distribution of this random variable n tau. So to that end, the first observation is that pk tau, the probability of exactly k arrivals in interval 0 to tau, I can rewrite it in terms of n tau. It's a probability of n tau equal to k. Probability of number of arrivals in interval 0 to tau equal to k. So this pk tau, I can write it in terms of random variable n tau also. So this n tau, that's why the heading is the number of arrivals. So n tau denotes the number of arrivals in an interval of length tau. Okay. So next, what we have to find is the distribution of n tau. That's the next task. We have to derive what is the distribution of random number of arrivals in interval 0 to tau. To see what is the distribution of n tau, the number of arrivals in the time interval 0 to tau, what we will do is that you look at the time interval 0 to tau in this picture, you subdivide it into equal intervals of length delta. So delta is very small compared to the tau, delta is very small. So we will have tau by delta number of intervals. If you have any difficulty, you imagine that delta equal to tau by n. N is some integer. I don't want to use the notation n there. because in the Bernoulli process we have used x1, x2, xn like that. So I don't want to confuse you with that notation. So we will keep using the notation delta. Delta is very small. So we will have n delta. Small n delta is the number of subintervals. So delta is the length of each subinterval. Delta is very small. And the probability P1 delta is the probability of exactly one arrival in one subinterval of length delta, P1 delta. So that according to Bernoulli process property, third property C, this P1 delta, we call it as, let us call it as P delta. Okay. So P delta, small P delta. So that is approximately equal to lambda delta, right? Because lambda is the arrival rate. Arrival rate times the interval length plus some small error time of delta. So these two we have. So you can imagine each subinterval either no arrival or one arrival. The probability of higher number of arrivals is negligible. That's what the Poisson process, the third property says. So if you look at the entire interval 0 to tau, the number of arrivals in the interval 0 to tau is approximately the number of arrivals in number of arrivals in the first subinterval plus number of arrivals in second subinterval plus etc. In each subinterval, the arrival is approximately the Bernoulli random variable with parameter p equal to lambda times delta. So this argument shows that n tau, the number of arrivals in the whole interval 0 to delta, n tau random variable is approximately the binomial random variable, which is the sum of n delta number of independent Bernoulli trials, each with success probability lambda tau approximately, lambda delta approximately. So n tau is approximately binomial with parameters n delta and p delta. Okay. So this, let us call this fact as a star. N delta's distribution is approximately binomial. Now I want to see what happens when delta, the subinterval length, gets 0, then the subintervals gets finer and finer. So before taking the limit, we note that the mean of the binomial distribution, which is the product of number of trials n delta and success probability p delta. So this is because of all these properties, this n delta times p delta, we can see that it is lambda tau plus error time. So as delta tends to 0, this the mean of the binomial n delta times p delta converges to lambda tau. Tau is fixed here, fixed interval length. Okay. So this we can use, if you recall, the Poisson approximations to binomial we have seen. So that we need one condition. This condition is satisfied here. The product of the number of trials and success probability should converge to some fixed number lambda. Right? Here it is lambda times tau. Okay. So if this fact you substitute in the star. Star means n tau. The number of arrivals in the interval 0 to tau is approximately binomial. And now you take in this star equation, take limit as delta goes to 0, use the Poisson approximation of binomial, we get the fact that this n tau random variable is Poisson with parameter lambda tau. Lambda tau is the limit of this n delta p delta. So we conclude by saying that the number of arrivals in an interval of length tau is Poisson with parameter lambda times tau. The parameter of the Poisson depends on the length of the interval. In other words, given any k from 0, 1 to etc., pk tau, the probability of exactly k arrivals in that interval of length tau, is same as probability of n tau equal to k. So n tau is a Poisson random variable, means that this probability is e power minus the parameter e power minus lambda tau power k by k factorial. So that is the fact. So number of arrivals is Poisson. So this is analogous to the fact that for a discrete time Bernoulli process, the number of arrivals by time n. Right? That was a binomial with parameters n and p. Here it is Poisson. So analogous fact here. We now know that the number of arrivals n tau in an interval of length tau is Poisson with parameter lambda times tau. As a consequence of that is that the expected number of arrivals E of n tau is lambda tau and variance of n tau is also lambda tau. So if you take the interval length tau equal to 1, we get the fact, in particular we get the fact that expected number of arrivals in unit interval, in unit time, that is lambda. So lambda can be interpreted as in a Poisson process with rate lambda. Lambda is the expected number of arrivals in an interval of unit length. Now let us come to the first arrival time of the Poisson process with rate lambda. So let T denote, the capital T denote the first arrival time. So assume that, here we assume that our starting time is T equal to 0, small t equal to 0, the process is starting, and after that let capital T, the random variable which denotes the first arrival time. So here the important thing to note is that for any small t positive, the event that the first arrival happens after small t is equivalent to saying that there are no arrivals in the interval 0 to t. Right? So the event n tau equal to 0, the event nt equal to 0, the event nt equal to 0 is same as the event capital T greater than small t. So this fact we use along with the knowledge of distribution of nt to get the distribution of capital T, the first arrival time. Right? So you note that, so P of t greater than t is actually the probability of nt equal to 0. Now nt we know that it is the number of arrivals in the interval 0 to t. It is Poisson with parameter lambda times t. So therefore that probability of nt equal to 0 is e power minus lambda t. Right? So that's what we are getting. So from that we can see what is the CDF, the cumulative distribution function of capital T. Ft of t, which is probability of t less than or equal to t, right? It's 1 minus e power minus lambda t. And the moment, right, you can now distinguish that this is an exponential distribution. If you still don't remember the exponential distribution function of exponential, you can actually take derivative d by dt of CDF, you will get the PDF, which is lambda e power minus lambda t. Okay, it's not essential, it is enough to have CDF also. CDF or PDF both uniquely determine, either of these uniquely determine the distribution of the continuous time variable. Okay. So the conclusion is that the first arrival time is exponentially distributed with parameter lambda. So lambda is the same as the arrival rate of the process, the Poisson process. So as a result, the expected first arrival time is 1 by lambda and variance of the arrival time, the first arrival time is 1 by lambda square because of the exponential distribution property. Now that we have seen the definition of Poisson process and the number of arrivals, that is Poisson, we have seen, and the first arrival time is exponential. So let us see one example to illustrate these things. So we have two countries, maybe India, Pakistan, or any pair of difficult countries. Two countries in the border, we are having cross-border firings between the respective armies. Assume that firing happens as a Poisson process, and this Poisson process with the rate lambda equal to 6 per day. So we are just assuming that from the data you have a look at the data over a period of years, and you just looking at the average number of firings per day or per week, you get some number. I assume that these firings happen as a Poisson process with the rate 6 per day. Okay. So then this will give actually a lot of information. The mere fact that we are assuming that the firings happen as a Poisson process will give you a lot of information. First of all, if you are asking what is the expected number of firings in a week, so here I am taking day as the unit time. We can work with hour or week or year, month, anything, but let us fix day as the unit of the time here. So once you fix the day as the unit, lambda is 6 per day. So what you want is that you want 1 week, right? So it is 7 days. So we are looking at N7. N7 is the number of arrivals in 7 days or in a week, N7. So we know that N7 is Poisson. That we know N7 is Poisson random variable with lambda times lambda tau. Tau is the length of the interval. Right? So it is a Poisson with parameter 42. So the number of arrivals in a week is a Poisson random variable with parameter 42. So that give you the expected number really, because for a Poisson random variable, mean and variance both are equal to the parameter. So expected number of firings in a week is 42. So it is not that difficult. Now we come to the next illustrating fact. If you want to know in a week probability of having exactly 5 times firing, so k equal to 5. So probability of n7 equal to 5, because it is a Poisson distribution, what we get is e power minus 42, 42 power 5 by 5 factorial. If you have a you seek a computer or a calculator, you can actually find what is the probability. We are still in the same example where we are considering the firings coming as a Poisson process with rate 6 per day. Let's also ask the question, what is the expected first firing time? So this first firing time is our notation is capital T. We know that because it is a Poisson process, it is geometric with parameter lambda. Lambda is 6 here. So T is a geometric random variable. Let me erase it. So geometric is for binomial, so we have to correct it. So this first arrival time T, it is exponential random variable here. Okay, so it is exponential random variable with parameter 6, which is lambda. So for Bernoulli process, it is geometric. For Poisson process, the first arrival time is exponential with parameter lambda, which is 6 here. So that gives you the answer, the expected first arrival time, or the expected time of first firing happens is reciprocal of lambda, 1 by lambda, which is 1 by 6. But you have to also note that our unit of time is day, so it is 1 by 6 day. If you want the answer in hours, it has to be 4 hours. Okay. Then one may also ask the question, what is the probability that the first firing happens after 2 days? So that is exactly the probability that t greater than 2, right? 2 days. Day is the unit of time. So probability of t greater than 2. Now we know that t is exponential with parameter 6. So it is just e power minus 2 lambda, which is e power minus 12. So this we are using the fact that the first arrival time for a Poisson process is exponential with parameter lambda, where lambda is the arrival rate or intensity of the given Poisson process. Still on the same example, Suppose the government wants to look at a sample of what's going to happen, what is going on in the border. They want the data of 2 days from every week, say Jan 1, Jan 2, and Feb 1, Feb 2, and December 1, December 2. So we have 24 days, 12 into 2, 24 days. Government just want to see what is the expected number of firings on these days. This is just for illustration. They may pick any 2 days from all the months. Just fixed ideas, we are taking the first 2 days of every month. So they capital I denote this period of 24 days. So they are not consecutive days. They are first 2 days, then next month 2 days, like that. So I is that time period, which consists of 2 days from each month. Now, government wants to know if what is the expected number of firings in this period I of 24 days. So at least we can approach in 2 ways. One way is that we know that the arrivals in one particular day, say Jan 1, and arrivals in Jan 2, they are independent. And also they are identical because of the Poisson process property. The same is true for February 1 and February 2, December 1 and December 2. So what we can do is that you can stack all these days together. You can consider them as actually 24 consecutive days because of our independence and time homogeneity properties of the Poisson process. So expected what we need to find is actually expected value of N24. The expected number of arrivals in 24 consecutive days will give the answer you want. That's one way of looking at it. So then N24 is Poisson with parameter 24 times 6, which is 144. Okay, so that will give you the answer 145. 144 on average, that many firings in this period of 24 days. There is another way to look at this problem, is that see here the 2 days, Jan 1, Jan 2, they are consecutive days. So we have a period of 2 days each. So 2 days each, so 12 times 2 days, right? So each 2-day period is consecutive. So we can see that it is a consecutive period of length 2. So consecutive period of length 2, then you can look at N2, number of arrivals in unit time 2, right? 2 units of time. That N2 we know it is Poisson with parameter 2 lambda, which is 12. Now we are looking at 12 independent copies of N2 because of the independence property. So that is also, then you will get expectation of the sum of 12 independent copies of these Poissons, and each of these 12 Poissons has mean 12. So 12 times 12, 144 is the answer. So that is another way. Either you can stack all of them together and calculate the answer in one step, or you can stack only the consecutive days, then after that you add all the 12. So both can be done. So this property of stacking only the consecutive days, then adding also will be helpful in many problems. In fact, so what we are using here implicitly, or it will also be helpful, one fact will be helpful in future to do many other problems, is that suppose we have 2 independent Bernoulli random variables. Let me call it as Z1 and Z2. Suppose Z1 and Z2 are 2 independent Poisson random variables. Z1 with parameter say lambda 1, Z2 with parameter say lambda 2, and they are independent. So then we can show that, you may have already seen that also, the sum Z1 plus Z2 is also Poisson with parameter lambda 1 plus lambda 2. So this is the reproductive property of the Poisson random variables. You may have also seen the similar things for normal, Bernoulli, etc., etc. So this fact also we can actually appeal to this. So we are adding 12 of Poisson random variables which are all Poisson, the sum will also be Poisson. So that fact also can be used. We next see some further properties of Poisson process. These are consequences of the three defining properties of the Poisson process. The first one among these is the independence property. So if you recall, the second condition of Poisson process is the independence property, which states that the arrivals in disjoint intervals are independent. So as a result, I just want to illustrate it with a few disjoint intervals. Let's take the intervals say 0 to 10, 10 to 15 and 20 to 23. So these three intervals are clearly dependent, clearly disjoint. And you look at the arrivals in these three intervals. So the arrivals in the interval 0 to 10 is n10, assuming that the process starts at time t equals 0, so n0 is 0. And the arrival in the interval 10 to 15 is n15 minus n10. And finally the arrivals, number of arrivals in the interval 20 to 23 is n23 minus n20. So we have now three random variables. Each of them are Poisson, we already know that. So n10 is Poisson with parameter 10 lambda, and lambda is the rate of the Poisson process. And n15 minus n10 is Poisson with the parameter 5 lambda, and n23 minus n20 is Poisson random variable with parameter 3 lambda. We have three Poisson random variables with different means. So they are all independent, so mutually independent. So any function of, for example, you take the first two of them, n10 and n15 minus n10, any function of them, f of is independent of any function of the third one, g of n23 minus n20. Similarly, you can take any combination. I have just taken three intervals here. You can take any number of disjoint intervals, any number of finitely many disjoint intervals, and you will get arrivals in each interval. Any function of any number of intervals among them will be independent of any function of the rest of the arrivals in rest of the intervals. So this we can use explicitly or implicitly in solving many problems. One more important property of the Poisson process is the memoryless property. To see what is this, you fix one time, say small t positive, you fix, and there is a Poisson process going on. You have observed the process up to time t. T is fixed and small t. Okay? So you have observed the process up to time t, and your observation is recorded as event A. A is the event of observing the process up to time t. Then, after observing the process up to time t, let t bar denote the time after time t up to the next arrival. Okay, so we are not counting the first arrival from 0 to 0 onwards. We are counting the arrival time after time t. From t onwards, you see the process and see when is the next arrival happening. So that is t bar. Then take any s positive, small s positive, you can immediately see that the probability that from time, what is the next arrival happening, the duration of which is t bar minus t. So that t bar minus t is greater than s, given our observation A. We have already observed the process up to A. So this conditional expectation, use the conditional probability definition, P of A intersection B by P of B. So this is this. Then note that this A intersection B, that is the probability of t bar minus t greater than s and and our observation up to time t. So that is same as because of the independence. Right? So A is happening in the interval 0 to t, and rest of the things is happening in the interval t to t plus s. Because of that P of A intersection B term is the product of the probabilities, and that is the probability of no arrival or zero arrival in the interval t to t plus s. The interval is of length s. That's why we get the term P0s. Like you remember Pk tau, the probability of k arrivals in interval of length tau. So this is P0s, and probability of a term gets cancelled. So finally the required probability of t bar minus t greater than s is P0s, which is e power minus lambda s. If you want, we can write the 1 minus e power minus lambda s and so on. But this shows that this required probability is same as the probability of t greater than s. T, remember, t is the first arrival time. Right? You start from 0. What is the first arrival time? That is a capital T. So that the distribution of capital T and the distribution of t bar given your observation up to time t, both are the same exponential distribution with same parameter lambda. Now you take the special case where A, suppose you have observed that, you have observed the Poisson process up to time t, and suppose that there is no arrival in that time, 0 to t, no arrival. That means my observation is A equal to capital T greater than small t. Arrival. So in that special case, you substitute here, what we are getting is that the probability of t greater than t plus s, or equivalently the probability of t minus t greater than s given t greater than t, it's equal to e power minus lambda s. Okay. So this is the memoryless property of the exponential distribution, or we can say memoryless property of the underlying Poisson process. So your observation that there is no arrival till time t has no effect on when your first arrival is happening after time t. That's why it is called the memoryless property. So this is similar to the memoryless property of the Bernoulli process. There we had a memoryless property for the associated geometric random variable. Here it is the exponential random variable.